This will be the third lecture covering material from Chapter 4. And this lecture is dealing with redox chemistry. And what redox stands for is reduction and oxidation. I think it's a pretty important part of the book, especially if you're moving on into advanced topics like biochemistry. And biochemistry and maybe even some organic chemistry, you're going to, and definitely inorganic chemistry, you'll talk about oxidation reduction reactions quite a bit. Okay, and so if you only learn one thing from this part of the book in this lecture, I think the most important thing is to understand what oxidation means and what reduction means. And I think the title slide figure kind of does a good job of detailing that. Okay, so oxidation is the loss of electrons. So in this figure, we have compound A losing electrons. It's being oxidized. Okay, reduction is gaining electrons, and that term reduction it kind of means the opposite of what's happening, right? It's gaining electrons, but it's reduction. What's happening, and we'll see this later when we talk about oxidation numbers, the oxidation number is getting smaller. That's why it's called reduction. Okay. So if you just kind of remember, I remember reduction means losing, or excuse me, reduction means gaining electrons. It's kind of the opposite, right? So that's how I remember them. Okay, and then we'll also talk about terms reducing agent and oxidizing agent. And the reducing agent gets oxidized, so there's like another kind of oxymoron thing, right? Adding that word agent, it just kind of means the opposite, right? A reducing agent causes something else to get reduced, and it is being oxidized. An oxidizing agent gets reduced. An oxidizing agent causes something else to get oxidized. So in this case, B is getting reduced, so B is the oxidizing agent, and it's oxidizing A. And that's the other point I wanted to make, that you don't have something losing electrons to nothing, right? They don't just go off into solution. Something else has to take them, okay? And so you can't have oxidation without something else being reduced. So this material comes from section 5 and section 6. Most of the material we'll talk about will be from section 5, and then section 6 is sort of a small section, and it covers the types of redox reactions, and there's 4 that we'll cover. Okay. So as I mentioned before, oxidation and reduction reactions, that's where we get this abbreviation redox reactions, are characterized by the gaining or losing of electrons. Okay. And oxidation, again, it is the loss of electrons. That's probably the best way to think about it. It also involves combination with oxygen. That's why it's called oxidation. But we'll see when we talk about oxidation numbers why combining with oxygen would cause a loss of electrons. Okay. Reduction, again, is gaining electrons. Right. You can also think of reduction as losing O2 or gaining H2. Sometimes in biochemistry and certain cofactors, you gain hydrogen. It's not as easy to see the electrons that the cofactor is gaining, but it's easy to see the gaining of hydrogens on the organic molecule. Okay, but for our class, I think it's best to think of it as the loss of electrons for oxidation and gaining electrons for reduction. Right, so in these examples, if you have an ionic compound, Okay, you have, in this case, your metals, magnesium, non-metal would be oxygen. Magnesium's going to give up 2 electrons to oxygen, and you're going to get magnesium cations and oxygen anions, and that'd be an example of a redox process, right? Because magnesium's losing electrons, it's being oxidized, and oxygen's gaining electrons, it's being reduced. Okay, that's fairly obvious, because you have these the complete transfer of electrons. On a covalent compound, in covalent reactions, um, you can still have a loss or a gain of electrons, a transferring of electrons, but it might not be as obvious. So in this reaction, we have H2 and Cl2, and their electron distribution is shown at their non-polar covalent, right? So they're, because they have 2 atoms that are the same, so their electrons are shared evenly. Okay, when these react and form 2 molecules of HCl, now those are very polar bonds, and there's a very uneven distribution, right? More of the electron density around chlorines because it's more electronegative. Okay, that is a shift of electrons. So you have, in a sense, you have hydrogen giving up its electron to chlorine. In a case in H2, each hydrogen sort of has 1 electron there shared evenly. In HCl, its 1 electron is really mostly around chlorine. So this is an example of another redox reaction. Okay, how would you know that? And that's the case where you have to look at what's known as oxidation numbers. Okay. So the rules for assigning oxidation numbers are given. I believe this is from a different text, but I like this table for detailing how you assign oxidation numbers. And that's really how you're going to be able to tell whether a reaction is an redox reaction or not, is looking at the oxidation numbers. And if one of the atoms, I guess it would have to be 2, of the atoms change in their oxidation number from the reactant side to the product side, that's how you know there's electrons being transferred, and that's how you know it's a redox reaction. Okay, so general rules, and these are the ones that you're going to use first when assigning oxidation numbers. Okay, for an atom in its elemental form, and that's something like, for metals, just their solid state, their solid state. Oxygen, chlorine, hydrogen, okay, those are in their elemental form, the O2, Cl2, H2. The oxidation number is going to be 0. Okay, and so some of those elemental forms are pretty obvious. Others, you might have to just get some practice with these questions. Okay. For a monatomic ion, the oxidation number is equal to the ion's charge. So if you have a +1 metal, its oxidation number is going to be +1. Okay, if you have something that has a negative charge, its oxidation number would be whatever the negative charge is. And finally, the sum of oxidation numbers for all the atoms in a compound equals 0. Okay, the sum of the oxidation number values in atoms in a polyatomic ion, so a molecule that has a charge, so the oxidation numbers have to sum up to equal the ion's charge. Okay. So those are the general rules. For specific rules, they're shown here. Okay, group 1 metals, they're going to be +1s in all compounds. Group 2 are going to be +2 in all compounds, and that's really because those metals lose electrons, and they're left with a +1 or +2 charge when they form ionic compounds. Okay. Hydrogen is going to be a +1 when it's combining with nonmetals. Okay, and this is probably 99.9% of the time. Almost, I can't really think of many examples of hydrogen when it's in a molecule being anything other than +1. However, when it's in combination with a metal, so a metal hydride, or with boron, hydrogen oxidation number will be -1. Okay. And you might see examples of those, especially with the boron, but most of the time hydrogen is going to be a +1. Okay, oxygen pretty much all of the time in the examples we'll see will be a -2 oxidation number in compounds. The real exceptions to that are peroxides. So when oxygen is in a compound that contains an oxygen-oxygen bond, the oxidation number is going to be -1. And when it's in a compound with fluorine, when it's bonded to a fluorine, then it won't have a -2. Okay, but I don't know if we'll ever really see that in this class. Might see a peroxide or two in the problem set, maybe, I don't remember exactly. But you definitely won't, I won't put a peroxide on the exam. On the exam, you can really just think oxygen is going to be a -2 when it's in a compound. Okay. And then finally, the halogens, group 7A, are going to be oxidation numbers of -1 when they're in combinations with metals and nonmetals, except with oxygen. Okay, so that's the one exception there. Okay. Or with halogens lower in the group, and I don't really think we're going to see many examples of that. Okay, might see some, chlorines bonded with an oxygen, but I don't really anticipate you're going to see halogens bonded with other halogens lower in the group for redox reactions. Okay, so let's try some practice questions in assigning oxidation numbers. Okay. So the first one, it's SO2, right? We know nothing about sulfur. The rules for oxygen, though, it says oxygen is -2 in compounds. So there's two oxygens. Each are going to have a -2 oxidation number. That gives us a total of -4 for oxygens. SO2 doesn't have a charge. So whatever sulfur is has to balance out oxygen oxidation numbers, so that -4 to add up to 0. Okay, so sulfur in this case has to be a +4 oxidation number. Okay, say chromate, CrO42-. Okay, oxygen again, that's the one we know something about, is a -2. Okay, there are 4 of them, so that has to be a -8. Okay. The total for, if we add those up, the molecule itself has a -2 charge. So if we think of chromium's oxidation number as X, we can set up an equation where X -8 equals -2. And then if we solve for X, X would be a +6, right? So chromium's oxidation number in this molecule is a +6. Okay, let's try some of these others. Okay, so NH3, we know hydrogens and compounds are going to be a +1. So H. Okay, why is it doing that? We know that H is going to be a +1 in this compound. Okay. We have 3 of them, and there's no charge, so that has to add up to 0. So nitrogen has to be a -3 oxidation number. Chlorine, so this is an example we have chlorine bonded to 3 oxygens. Okay, so this is an example of a case where the halogen isn't going to have a -1 oxidation number. So oxygens, again, are going to be -2s. Okay, so we have, we can set up our little expression. So X is the oxidation number of chlorine plus -6 for the oxidation numbers from the 3 oxygens has to equal -1. Okay, so we can do the algebra here, and when we do that, we would get chlorine has to be a +5 oxidation state. That's another term you might hear, especially with metals. You might hear what oxidation state is this metal in, and that you just calculate the oxidation number, and the oxidation number is the oxidation state. Okay. SF6, moving on. Fluorine is a halogen. Okay, it's going to be a -1. Okay, that means sulfur has to be a +6. Cl2, this one's easy. Okay, chlorine, that's its elemental form. So the oxidation number here is just 0. Okay, and then finally CClH3. Okay, what do we know on this molecule? Well, we know hydrogens are going to be +1 in compounds. Chlorine is going to be a -1. It's a halogen. So our expression would be X -1 plus 3 equals 0. Okay, so we would subtract 3 from both sides and add 1 from both sides. So that would mean carbon has to be a -2. Okay. So how do you know when you have a redox reaction occurring? Well, there's electron transfer. Okay, and a lot of times you're not going to see those in the chemical equation. You're not going to see the electrons written out explicitly all the time. But how you know there's electrons transferring is you see a change in oxidation numbers. Okay, so in this example, it's a combustion reaction. We have methane plus oxygen going to CO2 and water. Let me get my highlighter. All right, so methane, CH4 plus 2O2 goes to CO2 and water. So that's a combustion reaction. Okay. Is this a redox reaction? Well, to answer that, we need to calculate the the oxidation numbers. Okay, this is a kind of a table that summarizes them. Okay, carbon in CH4 is going to be a -4 oxidation number. Hydrogen's +1. Oxygen in O2, that's its elemental form, so its oxidation number is 0. Okay, now when we go to CO2, right, oxygen now is going to be a -2. So right there you can see that there's a change in oxygen. It's a 0 oxidation state in O2, but in CO2 it's -2. Okay. So that means it is being reduced, right? It's the oxidation number is decreasing. That means it's gaining electrons. Okay. Carbon in CO2 is actually a +4 oxidation state. So carbon goes from a -4 to a +4. So it's being oxidized. It's giving up electrons, and the oxidation number is getting bigger. Okay. And we can count up the electrons here. Carbon's actually giving up 8 electrons in this example. Okay. And oxygen in H2O also has an oxidation number of -2. Okay. And we see that oxygen goes from 0 to -2. There are 4 oxygen atoms, So the gaining of 2 electrons times 4 is a total of 8 electrons. So the number of electrons lost has to be equal to the number of electrons gained. Okay, so let's try to practice identifying redox reactions. Okay, so the first one, calcium oxide plus CO2 goes to calcium carbonate. Do it on the slide here. Okay, so calcium should say oxygen. Well, we could start with either, right? Because calcium's a group 2 metal. In compounds, it's going to be a +2. Oxygen is going to be a -2. Okay, carbon here is going, well, let's try oxygen first. -2, and there's 2 of them, so carbon has to be a +4. Okay, now let's look at our compound. Calcium, again, and it's in a compound, it'll be a +2. Oxygen will be -2. Okay, there are 3 of them, so that would be -6 total, +4. So carbon has to be a, carbon again has to be a +4. So in this case, there's no redox occurring in the first reaction. Okay, if we look at the second, now we have potassium, and I'll go through this a little bit quickly. That's a group 1 metal, so that's a +1. Oxygen's going to be -2. And if we add that up, that means nitrogen has to be a +5. Okay. K2O, potassium's +1, oxygen's -2. N2, that's an elemental form, that's 0. And O2 is also an elemental form, which is 0. So in this case, we have oxygen is going from -2 to 0, being oxidized, the oxygen in KNO3, and the nitrogen is going from a +5 to 0, so that is being reduced. Okay, the final reaction, okay, when we're assigning these numbers, sodium will be a +1 in a compound, hydrogen's a +1, oxygens are -2. That means sulfur has to be a +6. Sodium in NaOH is +1, oxygen's -2, hydrogen's +1. Okay, sodium in sodium sulfate is a +1. Okay, oxygen's -2. Sulfur again has to be a +6. And H2O, hydrogens are +1, oxygen is -2. Okay, so in this case, we don't have any species that are changing oxidation number. So again, this is not a redox reaction. So a summary of some of the terms we're talking about. Okay. So if in this generic kind of example, X is transferring an electron to Y. Okay, we can say X loses electrons. Okay, we can also say X is oxidized, right? Losing electrons means you're being oxidized. We can call X the reducing agent because it's being oxidized and causing something else to be reduced. And also, in terms of oxidation number, X increases its oxidation number. That's why we call this term oxidized. Okay. Y, on the other hand, is gaining electrons. Okay, we can say that Y is being reduced. It's gaining electrons. Y is also the oxidizing agent because it's causing X to be oxidized. And Y decreases its oxidation number, and that's where that term reduced comes from. Okay. So let's try to practice identifying oxidizing and reducing agents. Okay, so the first example shown here, we have aluminum solid metal reacting with sulfuric acid going to aluminum sulfate and 3 hydrogen gas, 3 molecules of hydrogen gas. Okay. So if we assigned the oxidation numbers to everything, all these elements, aluminum, solid aluminum metal is going to be elemental form, 0. Okay, sulfur in H2SO4 is a +6. Hydrogens are +1. Okay, when we look at the products that are formed, aluminum now is in a compound. Okay, and in that compound, we could add up all the oxidation numbers for the SO4s, 3 SO4s that are there, and we'd find aluminum, each of the aluminums has to be in a +3 oxidation state. So it went from a 0 to a +3. Hydrogen now, since it's H2 gas that's in elemental form, it is 0. Okay. So what's being oxidized and what's being reduced? Well, aluminum is going from a 0 to a +3. Its oxidation number is increasing, so it's being oxidized, right? It's losing electrons, so it's getting a more positive. Hydrogen going from a +1 to a 0 is getting reduced. That's lowering the number, the oxidation number. That means it's gaining the electrons. So what is the oxidizing agent and what is the reducing agent? Well, remember, the thing being oxidized is causing something else to be reduced. So aluminum being oxidized is causing hydrogen here to be reduced. So aluminum is the reducing agent. The opposite is true for the hydrogen. Hydrogen here is being reduced, so it is causing aluminum to be oxidized. So this is the oxidizing agent. And I should mention this right now in the problem set. When it's asking you what is the oxidizing agent, what is the reducing agent, it wants you to put in this whole molecule, okay? So don't just put in hydrogen for if it's asking for the oxidizing agent. Put in H2SO4. That's what it wants, okay? Let's look at the second reaction. Lead oxide plus carbon monoxide goes to lead solid plus CO2. And we can kind of tell here you have something that's lead that's in a compound and it's going to its elemental form. There's going to be redox occurring, right? There's going to be a change in oxidation number. Okay, so when we assign these, we can see that lead starts as a +2 oxidation number and it goes to 0. Okay, the other thing that changes is carbon. It goes in carbon monoxide, it's +2. Carbon dioxide, it's a +4. Okay, so in this example, lead going from +2 to 0 is being reduced. It's gaining electrons. Those electrons are coming from carbon, which is being oxidized. So what's the oxidizing agent? What's the reducing agent? Well, in this case, PbO is the oxidizing agent, and CO is the reducing agent. Okay. And finally, we have 2H2 plus O2 going to 2H2O. Right? The hydrogen and the oxygen are elemental forms on the reactant side, so those are going to be 0 oxidation numbers. When they're in water, hydrogen's a +1, oxygen is a -2. So we can tell that this is redox. There's redox going on. Okay, so what's being oxidized? What's being reduced? Well, oxygen going from 0 to -2 is being reduced. Okay, that oxidation number is getting smaller, which means it's gaining electrons. Hydrogen is being oxidized. Okay, so the reducing agent is H2. It's being oxidized. It's causing oxygen to be reduced. Oxidizing agent is O2. Okay, it's causing H2 to be oxidized. Okay, so there's a section about balancing redox equation, um, and we'll go through this a little bit. I don't know if I like this section in the book all that much, but it could be helpful um, for some of you to as a way to balance these equations. I probably won't really assign problems on this method. Definitely, probably, I would say not on the test. I'm gonna try to steer clear of. You might have to balance equations on the exam. So let me kind of back that off, as we do in chapter 3. But as far as balancing the redox equations, like the methods they give in this book, probably not going to assign questions like that. And especially with what they call the half cell method, which I don't think we'll really cover at all. I'm not going to assign those. Okay. Well, the first step, if you're going to balance a redox equation, is to assign oxidation numbers to all atoms, and that's kind of the first step of determining whether something is a redox reaction or not. Okay. Second step, you identify reactants that are oxidized and ones that are reduced. Okay. Then you have to see how many electrons are being transferred, and you draw those tie lines like I've been showing in the slides. That's really helpful. Okay. Then you need to make sure that the numbers of electrons that are lost by one thing equal the number of electrons that are gained by the other thing. Okay, and to do that, you multiply the number of electrons by a certain factor so that they're equal. If they're not already equal, okay. You use that factor to balance the coefficients that were in that chemical equation. Okay. And then you complete by balancing by inspection. Okay. So if we just try an example of some of these, right, the first equation we have copper solid plus nitric acid going to copper nitrate plus NO2 plus H2O. Okay, so we'd have to assign oxidation numbers to everything. You can kind of go through that if you wanted to pause this and make sure you know how to do the oxidation numbers. I think that feel free, but I'm just going to show them here. What you can see here is that copper is increasing in oxidation number, meaning it's losing electrons, being oxidized. Nitrogen, going from a +5 to a +4, is being reduced. Okay, so in this example, copper is oxidized, nitrogen in HNO3 is reduced. Okay, so this third step is to determine how many electrons these processes are using. So copper is losing 2 electrons. Nitrogen is gaining 1 electron. So then we have to do, in step 4, we have to multiply HNO3 by 2 so that the number of electrons lost by copper equals the number of electrons gained by nitrogen. Okay, when we do that, we have to look through the rest of the problem to make sure that everything else is balancing. Okay. All right, let's try this again with the second reaction. Sulfite plus O2 goes to lead oxide plus SO2. Right. So as we assign our oxidation numbers. Okay. In this case, we have sulfur going from -2 to +4. That's oxidized. Oxygen's going from 0 to -2. That's being reduced. Okay, how many electrons? Well, sulfur loses 6 electrons, and oxygen is going to gain 2 electrons per oxygen. Okay. So we have to multiply to make the electrons lost equal the electrons gained, so we put a 3 in front of O2, and then we have to balance the other products by inspection. So if we have 3 in front of O2 here, right, then that's going to be a total of 6 oxygens. So we'd have 1 and 3, so we'd have a total of 3 oxygens without, probably better to highlight it here. So 1 and 2, that'd be 3 oxygens. This is 6, so we'd basically need double. So we would put 2's in front of both of these. When we do that to balance, we'd also need to put a 2 in front of the lead sulfite. Okay. Oxidation reduction half reactions. These are, I think, kind of a good way to show it, because you're showing the oxidation or the reduction in single steps. In reality, they don't occur by themselves, okay, but this is a good way to show you what is gaining an electron and what is losing an electron. Okay, so our overall reaction, if we had, and this is kind of like an experiment you do in the lab, you put a solid copper wire in a solution of silver ions, and what you'd get out is that silver, it's a displacement, so the silver is going to actually come out of solution, and the copper would dissolve into solution. So in this side we see this crusty kind of stuff is actually silver precipitating out and becoming solid, and the bluish color in the solution is the copper that's dissolving. Okay, this is actually a redox reaction. What's occurring is that you have these silver ions, silver plus, they're actually gaining an electron from the copper and becoming silver solid. Copper giving up that electron is going to a copper plus. Okay. I believe, yeah, this should be a superscript. It should be copper 2 plus. I don't know why these are subscript here, but that's a typo. That should be a superscript to copper 2 plus. Okay, right. So we can break these down into their what's known as a half reaction. Okay, for the oxidation, right, copper is being oxidized. It's giving up electrons. And what's occurring here is copper solid's going to copper 2 plus 2 electrons. Okay, so we show the electrons as a product or a reactant in these half reactions. Okay, the reduction half is silver plus an electron going to silver solid. And that's really all I wanted to say. The book kind of goes through a method of balancing based on half reactions, but I don't think that's important to discuss. But knowing the half reactions, that method, I think, can be helpful, especially in, again, in more advanced classes like biochemistry and inorganic chemistry. Sometimes you deal with these half reactions. You can have titrations, redox titrations. They occur just similar to a pH titration, where you have some color change at a particular endpoint. Okay, and that color change, instead of being with a pH, it's dealing with some sort of a potential. Okay, or I should say the color change associated with a particular oxidation state, in this case of a metal. Okay. You would solve these as you would any other titrations, okay, you would have a volume of your solution, okay, that you find in the titration. You multiply by the concentration of that solution to convert it to the moles of that compound. Then you would use the molar ratio that you have up here in your balanced chemical equation, right? So in this case, you have 2 moles to 5, okay, and you would convert from moles of one thing to moles of another, okay, and then you would, in this case, you're trying to find the moles of calcium itself, so you'd have to use the ratio of elements in the formula. Okay. Not going to go through any examples of that. I think you guys have been doing enough of that in this section of the book, but it just shows that this whole chemical problem solving approach is used in many different parts of this book, okay, and it all usually follows approximately the same steps, right? You get enough information to get the number of moles of one thing, you convert to moles of another thing by the molar ratio in a balanced chemical equation, and then you use that moles of the other thing that you're looking for, and then convert that into moles of an atom of it that's in it, or the mass of that thing, or even a volume. Okay. The last section we'll talk about in chapter 4 are different types of redox reactions. Okay. Okay, and there's 4 of them that we'll talk about. The first is a combination reaction. And this is where you have 2 or more reactants combining to form a new compound. So generically, we can just say X plus Y goes to Z. Okay, that'd be an example of a combination reaction. Okay. Second is decomposition. This is the opposite of a combination reaction. You have a single compound that's decomposing to form 2 or more products. So generically, this would take the form of Z goes to X plus Y. Okay. Third, displacement reactions. And these are the ones that you see in lab. You can have a double displacement. In a generic formula for this would be AB plus CD goes to AC plus BD. Okay, so in this case, you have B trading places with C. Okay, so B goes with D, and then C comes over and combines with A. Okay, that's double displacement. You have two things switching places. In a single displacement, you only have one. So in this case, it'd be X plus YZ goes to XZ plus Y. So Z is changing places. It's you could say that X is displacing Z from Y. Okay, and then finally, I think this is one of the easier ones, combustion. Okay, so combustion is when you're combining something with oxygen, burning something with oxygen, right? So if you burn like a fuel in your gas tank in the car, right, that hydrocarbon is combining with oxygen and you're forming CO2 and water. Okay, so that's always the products of a combustion reaction, at least when we're talking about hydrocarbons, is going to be CO2 and water. Okay, those are always going to be redox reactions. And that's because O2 is a reactant that has a oxidation number of 0, and it's combining in a compound for the product, which oxygen is going to have a -2 oxidation number. So those are always going to be redox reactions. Right, so here we have some examples of all of these. So in this case, we have potassium and chlorine, so potassium solid and chlorine gas. Right, we combine those two, and they form a salt, potassium chloride. So this is an example of a combination reaction. Okay, and the oxidation states are shown in blue and red here. Okay. Decomposition. This example shown is mercury oxide. Okay, that ionic compound. You heat that up and you get out a what's going on here is the oxygen gas is leaving and you're left with not solid but liquid mercury. Okay, and that would be an example of a decomposition. Okay. Displacement. Okay, so here we have a lithium solid metal, drop that into water. Okay, you see bubbles forming. What's going on there is actually hydrogen gas being displaced from the water. Okay, so you have lithium plus H2O going to lithium OH plus H2. So you're displacing hydrogen from water. Okay. Okay, so let's try an example of identifying the type of redox reaction in each of these cases. The first example, we have potassium chlorate or chlorite. I think that'd be chlorite because there's 3. Going to oxygen gas, O2 gas, plus KCl. So what type is that? Right, we have one thing going to 2 things. Okay, and we can kind of just assume here that these are all redox reactions, but if we weren't told that, we'd have to actually calculate the oxidation numbers. But this one's kind of easy because you have O2 being elemental form is 0 oxidation state, and in the compound it's a -2. So you know there's your redox occurring. Okay. You have one thing going into 2, so that's a decomposition. A second reaction, we have zinc plus copper sulfate, zinc solid, plus aqueous copper sulfate, going to zinc sulfate aqueous plus copper solid. So and this is an example of a displacement. Okay. The zinc is displacing copper in that compound. And you can, this is also, we can call this a single displacement. And then finally, iron plus oxygen going to iron oxide. This would be an example of a combination reaction. 2 things going to 1 compound. And displacement reactions are fairly important in chemistry. There's a whole, what's known as an activity series. And the activity series is based on what metals can displace other metals in solution. And so if we look at that example of adding a solid metal like nickel into, in this case it's an acid, an aqueous solution of acid, what happens is that nickel will displace H2 from the acid and form H2 gas, and the nickel will dissolve. Okay, and this is a redox reaction, right? Nickel is going from 0 oxidation state in the solid to +2 in solution. Okay, so oxidation numbers increasing. That means oxidation is occurring here. That also means nickel's a reducing agent. Hydrogen's going from a +1 in solution, that acid, to 0. That oxidation number is decreasing. That means reduction is occurring at hydrogen. It means it's an oxidizing agent. Okay. More reactive metal is going to displace the ion of a less reactive metal when it's in solution. Okay, and so this example we've seen before, copper metal will displace silver ions in solution. Okay. So in this example, we have these copper, what's happening, the redox that is occurring, the copper is going to give up electrons to the silver ions. Silver is going to, when it takes those electrons and gets reduced, it's going to be uncharged and in the solid form, precipitate out. And when that copper gives up electrons, it's going to be an ion and then dissolve into solution. Okay, so in this case, we say that copper is displacing sodium, or excuse me, silver in that solution. Okay, and that this is where the activity series comes in. You can rank these metals based on their strength as a reducing agent. Okay. And you'll see this series. You see this probably most importantly either in this class or in inorganic chemistry. Okay, and also this becomes important when we talk about reduction potentials. We won't cover that this quarter, but that would be next quarter in electrochemistry. Okay. Metals that are higher on the list are stronger reducing agents, so they can the metals that are higher can actually reduce metals that are lower on the list, give up electrons to metals that are lower. Okay, so the ones at the very top here are very reactive. Lithium, potassium, things like that, sodium, they can displace H2 from water. So if you drop solid, the solid form of any of these metals into water, you get very vigorous, almost explosive reactions because they are donating their electrons to the hydrogen in water molecules to form H2 gas. Okay. The ones that are a little bit further down the list can displace H2 from steam. So again, that's from water. They're donating electrons to hydrogen and water, but it has to be heated for this to occur. So it just needs a little bit more activation energy for those reactions to occur. So these are less reactive. Okay. These metals here can displace H2 from acids. So again, like the example we saw, if you drop that solid metal into an acid solution of protons, it'll form H2 gas. Okay. Then we have H2. Okay. And H2 is included in there, sort of as a reference. Okay. The metals below that in the activity series can't displace H2 from any source. Okay, so no reaction would occur with these, and they're things like copper, silver, gold. Okay, more of the precious metals, and mercury. Okay, so that is all we have for redox chemistry. The next topic that we'll be covering before the exam will be Chapter 5, and that's the ideal gas law.